important things for the next 5 to 10 years. So I would think kind of when I'm from pharmaceutical companies, the first thing is when the people take the drug. So when people take the drug, when the people get some disease, we take the drug. So this was the current status. But what we truly believe down the road for the futures, we can predict when the patient get the drug. We can predict when the patient get a disease. So we can have the intervention much early on. So if that is true, actually, in many of them, this is already happening in many of the kind of maintenance. The maintenance doing the so-called predictive maintenance, and we can predict when we really need to change the engine oils and change the kind of replace part of this kind of the parts to improve the performance. So this is one of the problems that we truly believe that will be happening in the futures. But to talk about this is kind of the next question is what's the important problems and what's the future. I'm just going to talk about the big problems, what I truly believe in the 5 areas. So these 5 problems, I'm going to talk about high-dimensional data distributions and how can we estimate this, because this is really truly the fundamental of many of the research problems. And later on, I will describe some of these potential open problems that we are looking for some of the collaborations. So we know for the generative AIs, and people can put the prompt and generate the pictures. But actually, generate the picture, the fundamental to generate the picture is to estimate underlying the densities of the data. So we already have many of the publications. They already have many of the publications. I'm not going to review this, but in high levels, these are key things we can view at the generative AI to understand the underlying the density. This is kind of the very challenging problem for statistics. And kind of during the past 2 days, during the past yesterday and today, many of the talks are related to this one. For example, in Annie's talk talking about the differential privacies, and in the kind of how can we get high-dimensional correlated data estimation? That's very challenging problems. And Susan just talking about the digital health. If we do the offline reinforcement learning, there's many of the missing data problems, and some of the patients even partially observed. How can we do the data imputation and correlated data imputation? That's another challenge. So think about this image generations is a part of this generated high-dimensional correlated data. During the past, statistics is very difficult to handle these problems. Right now, because the generative AI, they already have some good framework, some problem. I'm going to quickly review this and also talk about what's the implication in the statistics. So here is one of the approaches to doing this called a diffusion-based solution. The general idea is to map the pictures to some completed noise. And so to doing this is they go to one step after another, have the original picture and continue to add the noise. And then we can use a neural network to learn the backwards. So this approach put in the formulas is in a very simple formula like this one, and people probably familiar with this and have the kind of training step, and also kind of reverse learning the noise. That's another approach, kind of equivalently another approach called score-based solutions. And so because if we learn the high-dimensional densities, one of the challenges of learning the high-dimensional density without loss of generality, we can write it in the top. But the problem is handle the denominators, kind of is normalizing constant is a challenge. But on the other side, they take the derivative of the log PDF, we can get the so-called score functions, and the score function is take the derivative with respect to x instead of with respect to the parameters. By doing this, and once we have this derivative, the score functions, we can recover through the Lagrange dynamic. We can recover the whole high-dimensional densities. By doing this approach, have been achieved a lot of good success. I'm not going to through the details, but in general, kind of the training the problems in the high-dimensional is a challenge, and people, because they are so sparse, suffer from the curse of dimensionalities. And so the people do a little bit of diffusion process, and after this diffusion, and we can learn the density relatively more accurate. But the point for here is right now we have like kind of the good framework, put both of these approach under the same framework, under the stochastic differential equations. So what we talk about for here is the general form of the stochastic differential equation. And through the approach, and we can form the DDPM, the diffusion-based solution, in one of the special case as the one of the special case of the stochastic differential equation. Another approach, similarly with the score-based solution, is another special case of the stochastic differential equations. By doing that, there's a lot of good implications for statistics to learn the high-dimensional distribution. The one thing is we know that if the forward process is a diffusion process, the backward is another diffusion process. So this is one of the implications. The second implication of talking about for here is the ordinary stochastic differential equation. They can also equivalent to the ordinary differential equations, and by doing this, they can make the trainings much more efficient. So, and by doing this, I'm thinking one of the implications for the statistics, we can better understand these kind of generative AI properties and what they put in the stochastic differential equation framework. I think this area is kind of widely open areas that not many of the statisticians have been doing this kind of the statistical properties. Another kind of thing is also very important for us is kind of this conditional generation. These provide additional framework for the foundation models. And I know this morning people talking about the foundation model. During the past, people talking about the foundation model is primarily through the transfer learnings. But for here, this kind of the bottom equations and it kind of made us very exciting, and they provide an alternative framework. Think about the case is we are interested to talking about this kind of the xt condition on the y. The y can be considered about like the prompt, and I write down a bunch of the kind of one of the sentence to generate the astronaut and write the horse, and I want to generate the dog with sunglasses. All this information can be considered as a conditional information. In the field of the digital health, sometimes we measure the partially observed observations for the offline learnings. How can we conditional this information to generate the whole profiles? All of these things can be considered as a conditional generation. But the cool thing for here is the bottom of the equations. If you look at the bottom equation to generate the image, generate the pictures, or generate the high-dimensional correlated data, in the bottom equation, that only one part kind of contains the y information, all the others that without any of the y information. So which means we can train one of the foundation models to learn the score functions of log pxt by using a lot of data to learn this. Later on, we can add this conditional information, the y conditional x. And also, the most importantly, kind of this y conditional xt, the y is in the lower dimensions. It's a classifier, it kind of can be binary doing the classifications. We can use a much smaller data set to train these classifications at the bottom. So in that case, kind of this provides a good framework as a foundation model to alternative framework to the foundation models that we are kind of using this for many of the areas. So by doing this, kind of they're talking about a few important implications, and we can leverage, put in the generative AI and the framework for the stochastic differential equations, where the tools can handle the high-dimensional PDF and solve can provide profound indications of many of the statistical problems. And also importantly, they can kind of estimate in the high-dimensional density. They can estimate the precise kind of the data densities for this, and currently we are using this for the outlier detections, the image detection, and also for some of the kind of data imputations. So another approach is how can we continue to expand this? How can we continue to expand this work? So one thing to expand this work is traditionally doing the machine learnings and doing the data. People are doing the data augmentation in the AIs, and if we talk about one method can help to significantly improve the accuracy. People talk about data augmentation in the image. I can rotate this, but many of the data is not in the not in the image, just doing the rotations. For example, in the molecule structures, where in the 3D, we need to consider about the rotation and the translations. So with doing the traditional way, doing the brute force data augmentation is very challenging. But how can we build in this kind of symmetrical information into the machine learning framework that can provide a much more elegant framework? So in that case, that is the framework of extend this to the lead group, to the use the mathematical group theory to doing this in the lead group. And so the challenge for here is how can we leverage the group theory to doing this, and how can I still use the generative AI framework? So one part is that we know the translation and the rotations, many of the problem belongs to this SE3 group, special Euclidean group. And we need to redefine what the plus and the minus operations if we still want to use this diffusion process. The second part is how can we define these Brownian motions in this SO3, in these groups. So there's some of the work has been done, and we borrow this framework and helping in many of the areas for us in the generative AI. And by doing this, we can better understand the first problem in the high-dimensional densities. I'm briefly can talk about the first problems. I feel like this is really important, and for statistics, and many work can be done in the first areas. The second area is the data augmentation and the labelings. If we talk about data, actually we can safely claim probably like 99.99% of the data in the real world settings is unlabeled data. How can we better leverage the majority of the data is a very challenging problems. And people talk about kind of annotations and the labelings, but annotation and the labelings kind of in the traditional naive way probably not works very well. And we know the experts have a limited time to doing the work. And we also know each annotation is not equally important. How can we use our limited time from expert to annotate the most important data, most informative for helping us? That's the the problem that we want to try to solve. And for the past few years, we have been trying to do the research in this area. Annie and myself and other students have one paper published in JASA and helping to solving the relatively low dimensional problems. But in the higher dimension, in the in natural language processing, in the medical image, we're still looking for some of the solution in these areas. So this data annotation and the labeling. So the third part is the reproducible research. And during the yesterday and today, we talk about a lot of this kind of topic on the reproducible research. One of the challenge of the reproducible research is we don't know how large of this null hypothesis, the null space. And for example, if we know the linear models can have one model, have one alternative model, have two models, and the model space is relatively small, then I can know what's the kind of chance of the false positive. But on the other side, if we use some of the other methodologies like random forest, or some other method, it's very like a deep learning, tuning the parameters. We don't know how large of this null space. The larger the null space is, the larger chance we got the false positive. How can we systematically to quantify this? That's the very challenging and important problems for many of the drug discoveries for us. As yesterday, Peter made a very good point is how can we build the infrastructures to enable us to do this? We have some preliminary approach, like for example, use the kind of version controls to know what all of the model histories, and but how can we incorporate this and to better estimate how large of the model space will be explored that can better helping us on this reproducible research. So this is a third topic. The first topic, and we are interested in how can we better use the totality of evidence. Yesterday we have some talks on the multimodalities. We briefly touched on these problems, but it's far from kind of the satisfactory. And so, for example, how can we combine this literature data? And over the lunch we have talked about is during the past many of the statistical approach and are now handling the papers at the covariate. And these days we just use the paper, download the paper, and the paper have many of the descriptions, either track the information, use these published PDF files at our covariate information to predict the drug properties. And so we are doing something like this. And beyond this, we also want to combine all the evidence, the animal studies, preclinical studies, and to better helping us on this to form this totality of evidence, the multimodalities of the predictions. So in the end, we are kind of also very interested in the trust and this data sharings. And people talk about what's the number one waste for the companies, the waste kind of the talent of the people. The reason they have a significant amount of waste is because of the trust issue. Many of the trust issues. And I didn't see kind of if we can all the trust is the cost, and if we can better the trust the kind of this each other, kind of better trust the data source and better to the data sharings. That's one of the fundamental problems. How can we better leverage the algorithm to solving in this area? We are exploring some like a for example, the multi-party computation. The multi-party computation is we want to share the data, but the data can only use for one purpose, just can be used for one purpose. So for example, if I'm interested in the average salaries kind of these 20 people in the room, so very simple algorithm, I can generate these 20 random numbers, but I'm forced the mean is equal to 0. But these numbers is really, really large. For example, the first number is 13 billion and kind of have multiple decimal values, and added your salaries on top of these numbers. And so you will be more safe to share this data. after share this data, the average will still be the true average because this we generate these random numbers, we force the random number with the mean is equal to 0. But the story behind of this is there's some algorithm, and they can force the data can be used for calculation for only one purpose. We will calculate the mean is correct, but the variance is incorrect, the quantile is incorrect. So how can we better to serve this purpose when we share the data can only serve the one purpose? For example, the multi-party computation could be one of the solutions. Differential privacy is another part of the solution, but they also suffer some of the the limitations. But in general, this belongs to the directions. How can we better use the algorithms, data analytics, kind of helping us to quickly form the trust and the serve the purpose and for the data sharing. So these are kind of the top the 5 things that I would think about is important. So and we talk about the positions and what's the important for the individual statisticians. So I'm thinking kind of it's important to continue to think about what's the big problem to focus on the social impact. And among all of these things, I'm thinking it's also very important to train our people as statisticians. How can we make our students or the next generation scientists, or even include ourselves, be more curious? Once we become more curious and we want to better understand the science, we want to be better to understand the bigger pictures, we want to own the problem, we want to own the problems. I continue to feel like we see our people and our new hires. Some people only define themselves as statisticians, only focus on the number of questions doing the statistical work. But on the other side, some people define themselves as a scientist and want curious to understand the bigger picture. I was thinking how to continue to nutrite, doing the nutrition of our curiosity is a very fundamental thing and for our next generation statisticians. And the next one is we need to understand the kind of whole paradigm of the research is changing. I like reading the book, kind of the Sapiens, a brief history of humankind. And they talk about the human beings have the 3 revolutions. One of the revolutions is agricultural revolutions that make us from the huntings to the farmings. The huntings means like a couple of peoples and the small troops can do the work. But these days, when we're doing the science, it's not kind of hunting anymore. We are doing the farmings. Then in the broader collaborations with the bigger groups. And how can we continue to develop the mentalities, kind of think about these collaborations and better understand what other people do. That's the kind of really the fundamental and helping us to grow the kind of expand our influence. So the new training structures and the reward framework is also important, I think, to accelerate this. And the trainings is, I feel like many of, we probably need to continue to encourage our students, like some of the fundamental classes are very important. For example, the operation, the numerical optimizations, operation research, some of this, the work, the optimization is truly form the foundations. Many of the, actually all the AI machine learning problems can be formed as optimization problems. And also understand the optimizations not only help this kind of practical use, and also help our theoretical statistics. Think about like the Lasso, and in the Lasso on the Oracle property predictions, they use the form the KKT conditions and to prove this. And they also helping us on this, and also helping us on the kind of even think about the curvatures and this variance estimations. And many of these are got connected. So in the end, we'll probably also think about what our reward frameworks and how can we better reward people to doing the science and make a bigger impact just beyond the publishing in the top 4 journals. So I think that's it. And so thank you so much. I think 100 years ago we had I counted this number of peoples and exactly kind of this we have the same number of peoples compared with yesterday. Okay.
I have 2 questions. So being a person who on the driver's seat, I wonder why Eli Lilly want to invest to create this division of AI in your company. What you guys are doing? And what's the role you play in the drug development? That's first question. Second question, if we have better solutions or some smart solutions, is there any channel that we can really help, contact your company and help your company to deliver or, facilitate the research in your company? How we're going to do that, to process that? Do you have any suggestion or some insights to share with us?
So I'm thinking kind of share a little bit of stories. And originally we formed a team about 6 years ago. We are the people like 5 or 6 people, the PhD. Right now the whole team, just in the US, full-time employee, the PhD. In my team already have 30 PhDs, including kind of plus myself, from multidisciplinary. So the question, the reason that this group is increased is that we continue to demonstrate the values for the company. We just continue to think about what is the most important problems for the companies to use kind of analytic AI machine learning to address the problem. Just to give a couple examples, in the last year, we finished the first de novo design to generate the large molecule, to generate the drug, and helping the companies. This make one of the breakthrough. And also, originally, we focused on the digital health in some areas, and we developed some of the kind of the app and the solutions better to quantify the Alzheimer's disease and also the Parkinson's disease. Over the lunch, we talk about this. So to make a long story short, continue to focus on the big problems, starting from the companies, and deliver the values and demonstrate the values, talking to the people's kind of demonstrate the value. This is the reason our team can continue to grow. So this is one part. This is one piece. The second bit that you mentioned, the collaboration. Actually, we do have many of the collaborations with many of the folks sitting in this room, and we continue looking for some of the collaborations. I'm thinking the collaboration from 2 ways. One part is we continue to disclose what the problems that we are most interested in. In my personal GitHub, I already post kind of 20 or 30 of the statistical problems and what is relevant for us, and also from these informal channels. And so I'm pretty interested in the high-dimensional kind of density estimations that can help in the digital health in many of the areas. And after the presentation, many people talk with me, and we have formed these informal collaborations. At the same time, I also more than welcome, because I don't know what I don't know. A lot of time, the people just kind of meet with me and show, oh, this is really important research we recently did. And that's influenced a lot of my research. That influenced a lot of my research. For the past many years, I'm doing the treatment recommendation. That started from a very initial discussions with kind of Professor Michael Kosrock at the moment. They showed me one of the papers and cite kind of Susan's original paper. And so we started kind of working in this area. We started working on the areas and generated some of the research. And we even launched some small trials to verify this kind of this dynamic treatment regime in these algorithms.
Rich. So why have they talked at all about, how Amazon has that Amazon Scholars Program where different, so have you ever talked to the guys, the upper people at Eli Lilly about maybe having a scholars program? Because that really, I think Amazon is benefiting grossly, in a positive way, by their scholars program. So what's Lilly's plans for a scholars program?
I'm so glad you mentioned this. Actually, we just started to form this so-called Lilly Academia Network, and so we are kind of looking for some of the collaborations. Like if the professor taking the sabbaticals, and we are kind of starting to form this program to welcome to come to Lilly's and start to have this, and also spend maybe 1 day. If they're not taking the sabbatical, spend 1 day working with the Lilly on the project. During the past, we have been informally doing this, working with Harvard and working with some of the professors. And right now, we want to make this even more kind of formal, have the process of doing this. Yeah, thank you for mentioning this.
That's great. So maybe we move to next talk, and next talk will be given by Maxine.